Hello friend, welcome to this lecture. In this lecture we continue our study of stability of a given solution. So, if you recall in previous few lectures we have discussed this x dash equal to a of x here. So, it means that the stability of any solution will depend on the behavior or the eigenvalues of the coefficient matrix A, and then at the end we have discussed that the stability of x dash equal to a x plus f of t is equivalent to the stability of 0 solution of x dash equal to a of x. So, I can write down in 3 part. So, if all eigenvalues have negative real part, then it is asymptotically stable. So, and if at least one has positive real part, then unstable, and if say all the eigenvalues have less than or equal to 0 real part and corresponding to 0 real part, if we have Am equal to Gm, then it is stable. If Am is strictly greater than Gm, then unstable. So, this we have discussed in previous lecture. Now, let us move a little bit further, and now we consider the non-linear system of differential equation. If you consider both are linear differential equation, this is a linear differential equation and this is a non-homogeneous linear system of differential equation. Now, let us consider say the differential equation x dash equal to ax plus g of x, where the non-linear part g of x equal to g1 x2 gnx is small when x is small, and we are assuming that gix divided by norm of x, where I is from 1 to n, are continuous function of x1 to xn and vanishes for x1 to xn equal to 0. So, if you look at what is the difference between this and the previous one, the difference is this part g of x. Now, here we assume that, let us assume that gx is weak in the sense of corresponding to linear part. It means that here we are trying to say that the linear part is dominated over the non-linear part. So, here we simply assume that if x is small, then gx is also small. So, it means that we are trying to show that if norm of x x is tending to 0, if you want to show that gx is tending to 0, then we simply say that near the neighborhood of x equal to 0, this linear part, that is a of x, is dominating over this non-linear part g of x. So, for that this is the philosophy of this result which we are going to establish. Now, here how we can say that as x tending to 0, gx is also tending to 0, and for this we are assuming that gix divided by norm of x are continuous function of x1 to xn. So, here we are saying that continuous function of x1 to xn means if these are tending to 0, then gx by norm of x is also tending to 0, and it vanishes when x1 to xn's are all 0. Okay. Then here we also assume one more thing, that is g of 0 equal to 0. Then if g of 0 is equal to 0, then we can simply say that xt equal to 0 is an equilibrium solution of 4. In fact, if you look at here, equilibrium solution we can obtain by putting ax plus g of x equal to 0. So, it may have say several equilibrium solution, but we know that if g of 0 equal to 0, then at least one equilibrium solution is a 0 solution. So, it means that if z0 equal to 0, then 0 solution is one of the equilibrium solution of x dash equal to ax plus g of x. The key point here is to note down that in case of nonlinear system, stability of every solution may not be determined. That is the difficult part we can consider that. In case of linear system, you can determine the stability of every solution, but in case of nonlinear system you cannot check the stability of every solution, but rather than you can check the stability of an equilibrium solution. So, here rather than checking the stability of equilibrium any equilibrium solution, we are checking the stability of zero solution. The idea is that if we have some non-zero equilibrium solution, then we can just shift that equilibrium point near to 0, and we can say that the it is without loss of generality, it is sufficient to find out the stability of equilibrium solution, which is stability of equilibrium solution x t ideally equal to 0. We will see that how the stability of some other equilibrium solution can be determined with the help of stability of zero solution or equilibrium solution, that is zero solution. So, first thing we are looking here, the stability of equilibrium solution x t ideally equal to 0 here. So, here we observe this thing, this is very important thing, that in the case of nonlinear system stability of every solution may not be determined, but in some cases with the help of stability of zero solution of its linear problem, associated linear problem, we may discuss the stability of its equilibrium solution. In this regard, the following theorem is quite useful, and this is the theorem which we are talking here. So, here first we are assuming that the vector valued function g x by norm of x is a continuous function of x1 to xn and which vanishes for x equal to 0, and also we are assuming that g0 equal to 0, so that I can assume that 0 is a equilibrium solution of this. Then we have three part. First part says that the equilibrium solution x t ideally equal to 0 of 4 is asymptotically stable if equilibrium solution x t ideally equal to 0 of the linearized equation, that is dx by dt equal to ax, is asymptotically stable. So, it means that 0 solution of this system 4 x dash equal to ax plus g of x is asymptotically stable if the 0 solution of the corresponding linear part, that is x dash equal to ax, is asymptotically stable. And if you want to look at this statement in terms of eigenvalues, then we can say that the 0 solution of x dash equal to ax plus gx is asymptotically stable if all the eigenvalues of A have negative real part. So, that is our part 1. Now, part B says that the equilibrium solution 0 solution is unstable if at least one eigenvalues of A have positive real part, right. So, if at least one of the eigenvalues of A has positive real part, then linear system will have all the solutions are unstable solution, as well as this s dash equal to ax plus gx will also have unstable equilibrium solution x t equal to 0 here. Now, in C part, the stability of the equilibrium solution x t ideally equal to 0 of 4 cannot be determined from the stability of the equilibrium solution x t ideally equal to 0 for dx by dt equal to ax if eigenvalues of all the eigenvalues of A have real part less than or equal to 0, but at least one eigenvalue of A has 0 real part. So, this we need to understand in the sense that if you look at the part A and part B is similar to the part A and part B of the previous theorem, that all the eigenvalues are having negative real part, then in the linear equation x dash equal to ax and x dash equal to ax plus gx, here every solution is an asymptotically stable, here equilibrium solution is asymptotically stable solution. So, in the case of all the negative real part. Now, if we have at least one eigenvalue with positive real part, then every solution of x dash equal to ax will be unstable solution, and here we can say that the equilibrium solution of x dash equal to ax plus gx is an unstable solution. But in part C, when the negative real part of the eigenvalues may be 0, then this here we have obtained that here we have a condition that am is equal to gm, then we have a stable solution. But in this case x dash equal to ax plus gx may not be determined as we have determined for x dash equal to Ax. In fact, here we simply say that in that case when eigenvalues of A, some of the eigenvalues of A have 0 real part, then it will depend on Gx whether it will be equilibrium solution is unstable equilibrium solution or stable equilibrium solution here. So, we will prove part A and part B little bit later, but let us first focus on the part C. It means that when the some of the eigenvalues of A have 0 real part, then how this Gx will play a very important role. So, it means that here we want to consider this part C, that we will present two differential equation, different differential equation of the form x dash equal to Ax plus g of x, where the nonlinear term Gx plays an important role to decide about the stability of the equilibrium solution xt are equal to 0. So, first let us consider this system dx1 by dt equal to x2 minus x1, x1 square plus x2 square, and the second equation is given as dx2 by dt equal to minus x1 minus x2 times x1 square plus x2 square. And if you write down, I can write down this like this, that if we assume x as x1 and x2, then I can write down this x dash equal to, now I can write it here x1 x2, so it is x2 minus, so it is 0 and 1, and here we have minus of x1 times x1 plus x1 square plus x2 square, and in the second equation it is minus x1, so that is minus 1 and is 0, and here it is minus x2 x1 square plus x2 square, right. So, it means that here I can write this as x dash equal to A of x plus g of x. So, here your A is basically what, 0 1 minus 1 0, and g of x is given as say minus, I can take it minus out, x1 x1 square plus x2 square, and x2 x1 square plus x2 square. So, this is this thing. Now, if we look at the norm of x, which is say under root of x1 square x1 square t plus x2 square t, right, then I can look at the Gx by norm of x. So, let me write it here. So, Gx of upon norm of x will be what, I can simply write it is as minus say x1, and here it is under root x1 square plus x2 square, and here it is x2 under root x1 square plus x2 square, right. So, Gx upon norm of x. Now, can we say that it is a continuous function of x? So, as x1 and x2 tending to 0, so as x1 and x2 tending to 0, or I can say that norm of x is tending to 0, where norm of x we are denoting as under root x1 square plus x2 square is tending to 0, then we can prove that Gx upon norm of x is tending to 0, right. So, it means that the condition, and look at G 0. So, if you look at G of 0, then Z of 0 is nothing but 0 here. So, it satisfies the both the condition that Z0 is equal to 0, and Gx upon norm of x is a continuous function of x, and as x1 x2 tending to 0, then norm of x is tending to 0, and we can say that this term is tending to 0 and this will also tending to 0. So, Gx upon norm of x is a continuous function of x, G0 equal to 0, and Gx by norm of x vanishes when x1 equal to x2 equal to 0. So, it satisfies all the condition of the theorem, and now we want to say that here stability may not be determined with the help of stability of the linear system, that is x dash equal to A of x. So, if you look at the linear system x dash equal to Ax, where A is what, A is having 0 1 minus 1 0. So, if you look at what are the eigenvalues of matrix A, and here we can simply say that the eigenvalues of the matrix A are plus minus I, right. So, here the the thing will depend on the eigenvectors of matrix A, whether it will have two linearly independent eigenvector or not. So let me so you can say that the stability of linear system will be depending on the number of linearly independent solution of say 0 1 and minus 1 0. Now here you can say that one eigenvalues is 1 say I, and another one is lambda 2 equal to minus I, and these two are distinct, and hence there is a guarantee that we have two linearly independent eigenvectors. So it means that the linear system x dash equal to Ax has all the solution which are stable solution. So it means that here 0 solution is an unstable solution, and hence all the solution of x dash equal to Ax is an stable solution. But now look at the our linear and non-linear system, that is x dash equal to Ax plus Gx. Now we want to look at the stability of x dash equal to Ax plus G of x. So how to look at the stability of 0 solution? Then we recall this condition that for every epsilon greater than 0 there exists a delta greater than 0 such that norm of x of t is less than epsilon whenever norm of x t naught is less than delta. So here we have to calculate the norm of x of t, where x of t is basically what? X of t is we are writing it as x1 and x2, and here we are taking norm of xt as say 2 norm of x, that is under root x1 is square t plus x2 square t. So we want to find out the bound on x of t, the behavior of norm of x of t. For that we look at the differential equation and calculate this x1 dx1 by dt plus x2 dx2 by dt. So we multiply the first equation by x1 and second equation by x2 and simply add. So if you look at the first equation is what? So first equation is this. So x1 x2 minus x1 is square, x1 is square plus x2 is square. So that is what we have written here, that minus x let me look at here, let me calculate this quantity. It is what? X2 minus x1, x1 plus x1 square plus x2 square, it is here dx1 by dt, and dx2 by dt will be what? Dx2 by dt is equal to minus x1 minus x2, x1 is square plus x2 is square. So here we multiply by x1, so we have x1 dx1 by dt, which is nothing but x1 x2 minus x1 is square, x1 is square plus x2 is square, and here it is x2 dx2 by dt is equal to what? Minus x1 x2 minus x2 is square, x1 square plus x2 is square. So when you add these two, we have x1 dx1 by dt plus x2 dx2 by dt equal to minus x1 x2 will be cancelled out, minus x1 is square plus x2 is square, you can take it out, and we have x1 is square plus x2 is square again. So here what you will get, x1 dx1 by dt plus x2 dx2 by dt equal to minus of x1 is square plus x2 square whole square. So I can write it this as, now this I can write it, it is nothing but 1 upon 2 d by dt of x1 is square plus x2 is square equal to minus of x1 is square plus x2 is square whole square. So I can write this as d by dt of x1 is square plus x2 is square equal to minus 2 times x1 is square plus x2 is square. So basically if I can write it here, that's d by dt of norm of x of t square equal to minus 2 times norm of xt whole square whole square. So basically it is a differential equation in terms of norm of xt. So we can find out the solution here, and we can simply say that this is nothing but d by dt of x1 square plus x2 square is equal to minus 2 times x1 square plus x2 square whole square, and we can calculate the solution. Here we can assume that norm of xt, let us say that it is simply y, then it is given as d by dt of y equal to minus 2 times y square, and we know how to solve this equation, and we can simply say that it is minus 1 upon y. So it is minus 1 upon, let me write it here. So this I can write it. So here I can write it here as minus 1 upon y equal to minus 2 dt. So, minus we can cancel out plus c dy by dt. So, it is what? It is minus 1 upon y square with minus sign. So, this I can write it 1 upon y equal to 2t plus some c. So, I can write it y as 1 upon 2t plus c, and I can simplify this and we can write it our solution y as 1 upon 2t plus c. So, what we have obtained here, that is 1 by y equal to 2t plus c, let us call it c1, y equal to 1 upon 2t plus c1. Now, calculate this value of c1, where what is y here? Y is x1 square plus x2 square equal to 1 upon 2t plus c1. Now, let us assume that at we need to calculate this value of c1. So, at t equal to 0, what should be the value here? It is x1 square 0 plus x2 square 0 equal to 1 upon c1. So, if we write down the value of 1 upon c1, so c1 is equal to 1 upon x1 square 0 plus x2 square 0 here, then I can plug in the value here, and what is the value here? x1 square plus x2 square equal to 1 upon 2t plus c1, let me write it here, 1 upon this value, let us call this as c. So, this is c. So, 1 upon c here. So, this I can simply say that it is 2tc plus 1 into c. So, if we use this, then we can have this result, that x1 square t plus x2 square t equal to c times 1 plus 2 ct, and where c is given as x1 square 0 plus x2 square 0 here. So, what we have done here, we have find out the expression for norm of xt whole square. So, we know that if xt is stable, then norm of xt will also be stable. So, or xt is tending to 0, then norm of xt will also tending to 0. Since in denominator we have this 1 plus 2 ct and c is positive here. So, it means that this is never 0. So, denominator is never 0, and in fact, it is a positive value, and as t tending to infinity, then this value is always tending to say smaller than the previous value. So, we can say that this x1 square t plus x2 square t is tending to 0 as t tending to infinity for any solution x1 and x2 t of 6. In fact, here we have not obtained the explicit solution x1 and x2, rather than we have found the say bound of or the expression of norm of x square t. So, here we have shown that whatever be the solution in x1 and x2, then x1 square plus x2 square t is tending to 0 as t tending to infinity. And also we may observe this thing, that at any time t, the value of x1 square t plus x2 square t is always less than the value of c. Now, what is c here? c1 is x1 square 0 plus x2 square 0. So, it means that if norm of x0 is less than delta, then norm of xt is certainly less than this delta, right. So, it means that if I assume this delta as epsilon, then we can say that norm of xt is less than epsilon whenever norm of x0 is less than say delta. So, here we simply say that our trivial solution x1 t equal to 0 and x2 t equal to 0 is asymptotically stable solution. So, here the linear part and non-linear part both are matching together. So, it means that here linear solution in the linear part x dash equal to ax, solution is asymptotically stable, solution is stable, but the non-linear part have solution which is asymptotically stable. Now, look at the next thing, next system of differential equation, dx1 by dt equal to x2 plus x1 square plus x2 square, and dx2 by dt equal to minus x1 minus x2 x1 square plus x2 square, right. So, here also we can write down the corresponding system of linear equation. So, we can simply write x1 dash equal to so x2 dash here. So, let me write it here. So, this is what 0 1, and here it is minus 1 0 x1 x2 plus x1 square plus x2 square, here it is minus x2 x1 square plus x2 square, right. So, here there is a small mistake here, it is plus here. So, second equation is dx2 by dt equal to minus x1 plus x2 times x1 square plus x2 square. Okay, so here this is plus here. So, this is this thing. So, here if you look at your A is same as the previous one. If you look at A is 0 1 minus 1 0. So, it is 0 1 minus 1 0. So, here we have shown that the linear system is same, right. So, but look at the non-linear system. So, non-linear system is what? X dash equal to Ax plus g of x. Now, g of x upon norm of x will be what? G of x is given by this. So, gx upon norm of x, where norm of x is under root x1 square plus x2 square, is basically x1 square plus x2 square and x2 x1 square plus x2 square. So, one thing is very much clear, that here g of 0 is 0, means you put x1 equal to x2 equal to 0, then we can say that g0 equal to 0. Okay. And second thing is that gx upon norm of x is a continuous function of say x here. So, as x1 comma x2 is tending to 0, then gx upon norm of x is tending to 0 here, and it will vanish when x1 and x2 are all 0 here. So, now we do the similar thing and we just calculate the say d by dt of x1 square plus x2 square, and we want to show that it is given as 2 times x1 square plus x2 square whole square. For that you simply look at here, let me write it here, say x1 dash is equal to x2 plus x1 square plus x2 square. I hope it is okay. X2 plus okay. Now, x2 dash is equal to minus of x1 plus x1 square plus x2 square. So, we can write down x1 dash plus x2 dash is equal to these two will cancel out, we will have x1 square plus x2 square whole square, and then I can write this as 1 upon 2 d by dt of x1 square plus x2 square, then it is x1 square plus x2 square whole square, then this is nothing but d by dt of x1 square plus x2 square equal to 2 times x1 square plus x2 square. So, if you look at, there is only one difference, that here in previous problem it is all negative. If you look at here in previous problem it is negative here, and in this problem it is both the positive thing. This is the only change we have considered, and with the, when we do this kind of change, we have this equation dx by dt equal to d by dt of x1 square plus x2 square equal to 2 times x1 square plus x2 square equal to 0. And as we have solved earlier, we can solve it here also, and we have x1 square t plus x2 square t equal to c upon 1 minus 2 ct, and the expression of c is x1 square 0 plus x2 square 0. So, we can say that c is positive, right. So, now if c is positive, then at time t equal to 1 upon 2 c, right, then at time t equal to 1 upon 2 c, the denominator is tending to, in fact denominator will be 0. So, it means that as t tending to 1 upon 2 c, your expression of x1 square t plus x2 square t is going to be large and large, and we can say that as t tending to 1 upon 2 c, your x1 square t plus x2 square t is tending to infinity. So, here we are assuming this condition, first of all, that x1 and x2 of 7 with x1 square 0 plus x2 square 0 is non-zero. So, it means that we are considering any solution which is other than your trivial solution. Then we can say that every solution of x1 and x2 of the system 7 will tend to infinity in finite time itself. So, as t tending to 1 upon 2 c, your solution will be tending to infinity, and hence we can say that your solution, equilibrium solution x1 t ideally equal to 0, x2 t ideally equal to 0 is an unstable solution, right. So, here if you look at in both the equation number 6 and 7, your linear part is same, that is dx by dt equal to Ax, and A is the same matrix, that is 0 1 minus 1 0. But in previous problem we are getting the solution, 0 solution is an asymptotic stable solution, but in this problem we have seen that 0 solution is an unstable solution. So, it means that in case when the coefficient matrix have at least one eigenvalue with 0 real part, then the stability of equilibrium solution of x dash equal to Ax plus Gx may not be determined using the given theorem. That will depend on the behavior of g of x, and this theorem is not capable to give any conclusion in this regard. Maybe there are certain result available, but here we may not discuss the same result here. So, we simply say that when coefficient matrix have eigenvalue with 0 real part, then this theorem will not give the any conclusion, right, and everything will depend on the further analysis of the nonlinear part Gx. Okay. So, with this I finish our lecture. In this lecture we have discussed only the C part of the theorem, and in next lecture we will consider the remaining part. So, we will continue in next class. Thank you very much for listening. Thank you.